Now I can share my slides. All right, so hopefully you guys are able to see my slides. Let me know if you are not able to see them. Okay, so we get started with lecture 6 of matrix algebra. We're going to talk about bases and dimension today. So there are lots of terminology that is going to come your way. So I'm going to try my best to make all the terminology as clear as possible. We'll do some examples. So hopefully that gets through. All right. So this is sections 3.4 and 3.5 of the textbook. So before we talk about bases, we need to talk about spanning sets. So let's suppose that you have a W that is a subspace of Euclidean space R to the n, right? And there is a set S which has R vectors V1 through VR, and S, that set S, is going to be a spanning set of this subspace W if every vector that is in that subspace can be expressed as a linear combination of the vector that is going to belong to this, right? So you should be able to take any linear combination of these vectors and be able to express any vector in the subspace W. So I can write that down as this particular linear combination. So I have K1 through KR as some scalars that, so how much V1 do I need to get W? I need K1 amount of V1 to get W, K2 amount of V2 to get W. And if I add all of them up as a linear combination, I get the vector W, which belongs to the subspace. And if that is true, that set of vectors that I used for my linear combination are going to be considered as a spanning set for my subspace W. K1 through KR are scalars. What this informally means is the basis of W is going to be a spanning set, and it contains as few vectors as possible. As you can see over here, this particular set of vectors, there's no constraint on that, right? Like they are R vectors. That is a spanning set. But for a basis, for it to be a basis, it has to contain as few vectors as possible. What that essentially means is all these V1 through VR should be linearly independent. And if that is the case, then you can call that a basis. So let's take a look at a quick example over here. Let us say that we have some set of vectors. I have S as a set of vectors, and let us say I have two of them, U and V. And I'm going to define these U and V as 2, 3, 1, and let us say I have 1, 0, 5. So these are in R cubed. There are two vectors in this set S. And let us say that my W, the subspace, is span of S. This is capital S. What this means is, so the definition of span is any linear combination of the vectors in the set. So I should be able to, the subspace W is right now defined as you can take any amount of V1 or U and any amount of V and get to be in this subspace W. So W is your span of S. So let us ask a question here, which is let us define another vector here, W, which is say 5, 6, 7, that belongs to the same subspace cap W, right? So how do you check this? Well, if that has to be yes, the answer to that question has to be yes, then we should be able to express W as a linear combination of U and V, right? So let us try to see if that works out. So let's try to see that with, you should be able to get 5, 6, 7 by taking some amount of U and some amount of V. And if you get K1 and K2 that satisfy this non-trivial result, then we can say that W is going to belong to the subspace cap W, right? And you can see that these are going to be linearly independent, right? So for example, if I need this 6, right, I have a 0 from here and a 3 from here, which means that my k1 has to be a 2, right? So if I have k1 to be a 2, then I match up my second element over here, which is 6. Now if I use this 2, the first element is going to be 4 plus k2 should give me 5. So 4 plus k2 gives me 5, which means k2 is a 1, right? If this is a 1 and this is a 2, let me just check whether the last entry matches up or not. So you have 2 times 5 gives you 7. So yeah, that's perfectly okay. What that means is, yes, my small w vector that I chose, I was able to express as a linear combination of my set of vectors S, which means that my W is going to belong to the subspace W, right? So you just need to figure out if there are some scalars that will help you do this or not. Let's see. Let's move on here. What a basis is essentially it's a compact representation of a subspace. A basis. So when you're talking about a spanning set, there was no such requirement that all the vectors had to be linearly independent. But for a basis, for it to count as a basis, all the vectors have to be linearly independent. And what that results in is a spanning set which has as few vectors as possible. So basis, in other words, is the smallest spanning set of a subspace. And we'll prove this more formally as we go on. Now, how do you row reduce to find that smaller spanning set, right? So smallest spanning set is your basis. How do you do a row reduction and get there? So let's take a matrix A here, and we saw this earlier. You can do the row operations to row reduce it to B. B in this case is your row reduced in a row reduced echelon form. And if you do row operations, we know that the row space doesn't change. So the row space of A and B are going to be identical. So if you take A to be this matrix over here, which is 3 by 4, and you row reduce it, which means that you're doing all those row operations to get your leading ones, and then in those columns you are making zeros. So you got the leading ones over here, and you had all the zeros in those columns. And this row reduced matrix over here, we are calling that B, right? So A is your original matrix. The row reduced echelon form equivalent is B. So as you're doing those row operations, we saw in the last class that the row space doesn't change. So row space of A is going to be what? You have one vector here and the other vector here and the other vector here. So row space of A is going to be the span of each of these rows. So essentially what that means is row space, if you want to reach any thing in the row space of A, you can take some amount of the first row and some amount of the second row and some amount of the third row, a linear combination, and get to anything in the row space of A. But also after the row reduction, you can do the same thing. You can reach the same space with only two vectors. So as you can see in the row reduced form, you only have two non-zero rows. The first one, 1, 3, 0, 1, which is right here, and the second one, which is right here, which is 0, 0, 1, negative 2, right? So whatever you can reach as a linear combination with three vectors, you are able to do that with just two vectors, which means that one of those other vectors was not giving me any new information. It was a linearly dependent row. So over here, the span of A is the same as the span of the row reduced row space. So we started off with a matrix, we row reduced it, and we saw that the row space is not changing. In fact, the row space, you can express it as a spanning set with three vectors, but simply it is spanning set of two vectors. So if you wanted to find out the basis of this matrix, you're going to, basis for the row space of A, you're going to say that it has these two vectors in the basis, right? So this essentially means that basis of row space of A has two vectors, this guy and this guy. Because we are going for the smallest spanning set. We cannot use 3. It's not the smallest. We can use 2. All right, so let's see. And you can sort of see this, right? The third row is sort of a linear combination of the first and the second one. If you did the first one minus the second one, you get the last one. So the last one is not giving me any new information. So I was able to sort of get rid of one of them. All right, so let's see. How do you check whether a set of vectors will span your R to the n Euclidean space? So let us start with some set of vectors S. It has 3 vectors over here. Each of them belongs to R to the R cubed. Now the question over here is, does S, this particular set of vectors, span R cubed? Right? So can I take a linear combination of this guy, this guy, this guy, and be able to reach anywhere in R cubed? Right? So what this really is asking is, can I take, let me just define these here. So let me say this is my V1, this is my V2 vector, then this is my V3 vector. So the question is, can I take K1, can I take K1 V1 plus K2 V2 and K3 V3? And if I do that, can I reach any B, right? Any B, any solution. So can I reach any B1, B2, B3? Because that is going to be, of course, belonging to R to the 3, right? So the question is, the span of these 3 vectors, can you reach any B? That's the question. So in order to solve this, what we'll do is we'll try to determine this, right? So essentially this problem is being translated as AX equal B. And if there is a solution here for B1, B2, B3, then that can only happen if this is going to give you a consistent solution. Some solution has to be there, non-trivial one. So let's see. So AX equals B. So A is going to be the columns 1, 2, and 3. So we are essentially writing out this particular condition, but as a matrix formulation. That's all we are trying to do here. So I have got the first vector here, the second vector here, and the third vector here, and I have formed the augmented matrix with B1, B2, B3, right? So just to clarify, you see, I've got K1 amounts of V1 plus K2 amounts of V2 plus K3 amounts of V3 equals this, right? That's what I was trying to go for. And you can sort of rewrite this as V1, V2, V3 multiplied by K1, K2, K3. Does that give you B1, B2, V3? And so it's like AX equals B, right? So we are trying to find out, is there a set of Ks that will satisfy this? So we are trying to formulate the augmented matrix and then go for row reduction. So the augmented matrix will have all these 3 columns, right? 1 here, 2 here, 3 here. And then we'll pad it with the right side coefficients, B1, B2, B3. Now if you carry out the row reduction, this will be your echelon form, a row reduced form. So what we can say from this is, if this has to be consistent, which means that there is a vector B1, B2, B3 that you can get to, then all of this has to be, well, you got an identity actually, right? So you got an identity, which means that you can pick any choice of B, right? B1, B2, B3, you will have a solution. K3, for example, K3 will equal that, K2 will equal that, K1 will equal, or K1 minus K2 plus 2K3 will equal that, which means I can come up with any linear combination over here to reach any B, right? So that means that this system is consistent for any choice of B, any choice of B1, B2, B3. So S will span all of R cubed. However, if you notice here, if this guy was a 0, right, if this guy was a 0 here, if this guy was a 0, then we would have a constraint on this. So we would need that to go to a 0, which means that now it's not going to span all of B cube. The span is going to, the span of that is going to be limited to certain values of B1, B2, B3, because that has to be a 0 in that case. So if there had been some B for which the system was inconsistent, that B should have this going to a 0, then S wouldn't have spanned R cubed. All right, questions here? So as long as we were over here, until any B1, B2, B3, with this being a 1, you could reach anywhere, right? So if you wanted to reach, say, 1, 2, 3, B1, B2, B3 are 1, 2, 3, you can put it over here, and you know you will be able to reach there. All right, you can find K1, K2, K3 to reach there. But if you had something in which B3, all of this was going to a 0, you would not be able to reach that. So the system wouldn't have spanned the entire R cubed space. All right, let's move on to the formal definition of a basis. So if you have a W, which is a non-zero subspace in R to the n, then W, the basis for this subspace W is going to be a linearly independent. So this is very important. It has to have linearly independent vectors, but also they have to span. It has to also be a spanning set. So two things have to happen here. One, the basis has to have linearly independent vectors, and those vectors, a linear combination of those vectors, you should be able to span anywhere in W. And if that is the case, then those vectors are going to be defined as my basis. Now the question is, why do we require linear independence? It is easy to see that we need spanning set because we need to reach any point in the subspace. But why do we need them to be linearly independent? So in order to check, to look at this, what we'll do is we'll try to assume that there are some, it's not completely independent. So there is some vector in there which is linearly dependent on the other vectors. And we will see if that still gives me a basis or not, right? So let's try to see if our set S had these vectors v1 through vr, and I'm going to assume here, let me do it in red. Assume that my S spans W, right? The subspace is spanned by these vectors v1 through vr, which means that any linear combination of these vectors, I should be able to get to this anywhere in the subspace. So if this set of vectors, so we are doing this proof by contradiction. If this had it was linearly dependent, right? So these vectors are not completely independent. There is a vector in there which is linearly dependent. Then we can write one of these as a linear combination of the others. So what we'll try is exactly like this, right? Earlier, we wrote this guy as a linear combination of the first two, which meant that that set did not have linearly independent vectors. It was dependent. But when you went here, now it had linearly independent vectors. Let's go back and check here. Yeah, so linearly dependent, what we can say is, let us assume this VR is dependent on all the others, V1 through VR minus 1, some linear combination. So what we can do is we can assume that VR is a linear combination of others, which means that we can write VR as some linear combination of all the remaining vectors, V1 all the way to V sub R minus 1. Now let this vector W belong to the subspace W, which means that we will have some scalars D1 through DR for which we can reach this anywhere in the subspace. So I'm going to define my W, because it is a spanning set. W is a linear combination of all the vectors, right? W is belonging to my subspace W, cap W. Next, for this VR, I said this was linearly dependent on all the other vectors. So I was able to write that statement. I can substitute that VR over here, which means now I've got this. Now, if I've got this, I can start combining the coefficients of the vectors. So for V1, you have got D1 plus DR. And then for V2, you have got D2 plus DR K2 actually, right? For V1 here and here, the coefficient is going to be, the scalar is going to be D1 plus DR K1. That went over here. And then for D2, similarly, it's going to be D2 plus DR K2 and so on. So what you have over here is what? This is a linear combination of vectors V1, V2, all the way to VR minus 1, right? Which means that whatever I was able to get to with VR, I'm able to get to with just R minus 1 vectors. So this is not the smallest set. This one is going to belong to the same spanning set, but I really don't need that VR vector because of that linear dependency on all the other vectors, which is why we need this. So that means that it is not the smallest set. For it to be a basis, it had to be the smallest spanning set. So in this case, we can throw out VR. So that sort of proves that why we need them to be linearly independent. All right, so that's your definition of the basis. Smallest spanning set in which you have linearly independent vectors for a subspace. The natural basis is probably the most straightforward basis. This is going to be the set of unit vectors, and you can very easily see that you can span anywhere in the subspace with unit vectors, and also they are linearly independent. So in these vectors. So if you did it for a natural basis for R squared, you would have vectors 1, 0, and 0 and 1, right? And if you did it for R cubed, you would have the natural basis or the basis vectors as 1, 0, 0, and you know the deal here, 0, 1, 0, and then you will have a third one there, 0, 0, 1. So these are unit vectors. So in general, what you can say is, if you have a set of vectors E1 through En, that is going to be the natural basis for R to the N. So that particular set is going to be linearly independent, and it's very easy to see this, right? You have 1 over here and a bunch of zeros, and 0 over here, a bunch of zeros. The ones are never lining up, which means that they are going to always be linearly independent. So wherever you want to get to, you will need some amount of one, some amount of second unit vector, some amount of the last unit vector. And you will be able to get to any, because you can take any amount of x1, any amount of x2, any amount of xn, which means that it is going to be both spanning set and also linearly independent, making it the basis. And the basis over here has unit vectors, and we are calling that by the special name natural basis. So if you assume that there is any vector x here that belongs to R to the N, like that, you can reach there with all these unit vectors, x1 times this. How much of E1, how much of E2, how much of En? Well, x1 amount, x2 amount, xn amount. You will be able to reach there. So you can write this any vector in R to the N as a linear combination of these unit vectors, which means that they form the natural basis. They are the smallest spanning set with linearly independent vectors. And we will later on show that this particular set S is linearly independent. So whenever you're starting to see these zeros, right, you will be able to quickly check whether they are linearly independent or not. And we'll prove this more formally later on. Let's see. Questions so far? Natural basis, set of unit vectors. They span all of R to the N. So if I had these vectors, right? So for example, if I was working in R to the 3, R cubed, if I took these 3 vectors, and if I took some amount of E1, some amount of E2, some amount of E3, I would be able to reach to any vector in R to the 3. And that's the smallest set for which that can be true. All right, so my natural basis is going to be a more straightforward result there. All right, now let's talk about the basis for the null space. So we know that the null space is what? The null space is solutions to ax equals 0, right? So if you have a homogeneous set of equations, any x that satisfies this is going to be it's going to be defining your null space. And we also saw that null space is a subspace. Now essentially what we are trying to determine is what all x's will satisfy this. So whatever vector x over here satisfies this, can you represent that as a basis? Which means, can you represent that null space as the smallest linearly independent spanning set? Right, that's the question here. So let's try to work with an example that we had already worked with. So we started off with a set of equations, and we were trying to find, we worked with these equations in the previous lecture, but let's start again. We are trying to find a basis for the set of solutions to these two homogeneous equations. So you've got 6 variables in here, and you can set it up as an augmented matrix, and then you can do the row reductions. When you do the row, and we have done this in the previous class, what we got for the solution set was this: any vector x that belongs to R to the 6, because we are going to need 6 values, there are 6 variables in there, any vector x that belongs to R to the 6 such that the first element is this, the second element is s. So how are we getting these? Well, you have these, you will get that once you start doing the row reductions, you will see that x1 and x3 will become your leading variables, and you can associate say s with this. Let's see, no, those are your leading variables. X2, all the others will be your remaining variables. So x2, x4, x5, x6, all of these are remaining variables. So what we can do is we can associate some arbitrary values with our remaining variables to find a constraint on the leading variables. So STUV, that's what we had picked for x2, x3, x2, x4, x5, x6. STUV, that's what you see here. STUV for x2, x4, x5, x6. And once you do that, you will get the corresponding x1 and x3 as this and as this. So any vector that you get in this particular form for the given STUV will belong to the null space of A. So how do you, from here, how do you get to the basis? Well, you do this. You try to manipulate this x vector into 4 different vectors. How are you doing that? You're saying x is, simply you are going from here to here. You're pulling out an s, and we are saying, what is the coefficient of s here? 3, 1, 0, 0, 0, 0. You've got that vector. And then what is the coefficient of t? -4, 0, -3, 1, 0, 0. You've got that. And similarly, you have done it for the other the u and v as well. So my null space now is going to be, you can take s amount of this vector, t amount of this vector, u amount of this vector, v amount of this vector, and you can reach anywhere in my null space. Null space is solutions to that equation over there. So these 4 will have to satisfy 2 properties, right? One is what? They have to be all linearly independent, and we'll prove that in a minute. The second one is they have to be a spanning set. And we went from the solution set to these vectors. So if you think backwards, yes, they are going to span all of the null space. So let's try to add a page here and check whether you get these vectors, are they linearly independent or not, right? So to finish this, what is my basis? What is my answer? Basis of my null space? Basis of my null space has 4 vectors. Vector 1, vector 2, 3, and 4. They belong to a spanning set, and they are linearly independent. So that's the smallest spanning set with linearly independent vectors. So let's try to sort of see whether they are linearly independent or not. I will add a square wave page here. All right, so I'm going to do this and check whether they are there or not, right? So let me define these vectors here. The first vector in my basis was 3, 1 followed by 4 zeros. And the second vector was -4, 0, -3, 1, 0, 0. I'm just rewriting these 4 vectors over here to check whether they are linearly independent or not. And I hope they are, right? So that's the only way I can claim that it is in the basis. And the last one is going to be -1, 0, -7, 0, 0, and 1. So let me just call them by certain names. I will call them W1 a vector, W2 a vector, W3 a vector, W4 a vector, right? So the question here is, are these linearly independent? So you can ask the question in slightly different manner. You can ask the same question by asking, are there non-trivial solutions to some amount of W1 plus some amount of W2 plus some W3 plus some W4, some W4, do you get the zero vector or not, right? So if you get the zero vector if you get non-trivial solutions to this, that means that they are going to be linearly dependent. If you don't get, if you only get a trivial solution to this, then you know that they are linearly independent. So let's try to see how we can check whether you get trivial solutions or non-trivial solutions. So I need to essentially find out x1, x2, x3, x4 so that this is satisfied, right? So let's try to do that. So if you take x1 amount of this plus x2 amounts of this plus x3 amount of this, x4 amount of this should equal a bunch of zeros, right? 6 zeros. Which means you can write this new system of equations based on that. The new system of equations is going to be x1 amount, 3x1 minus 4x2 minus 2x3 minus x4 equals 0. That will be for the first elements in the vectors. And then similarly, you will get x1 equals 0. You get -3x2 plus x3 minus 7x4 equals 0. And then you get x2 equals 0. Then you get x3 equals 0. Then you get x4 equals 0, right? So I'm essentially putting in these vectors over here and equating each of them to 0. So if this is the case, you see x4 has to be a 0, x3 has to be a 0, x2 has to be a 0. And if you plug that in over here, okay, 0 equals 0, that satisfies. X1 is 0, you plug it over here, all of this has to be a 0. So you can see that the only way this system of equations can be satisfied is if it is the trivial solution. So only solution is the trivial solution, which means x1 equals x2 equals x3 equals x4, which all of them have to be equal to 0, which means that there are no, are they non-trivial solutions? No, there are no non-trivial solutions over here, which means yes, they are linearly independent, right? So we said that it is a basis, so it had to be linearly independent vectors, and we proved that it is linearly independent vectors. Questions about this example? All right, let's try to move on here. So let us try to find a basis for the range of the matrix. You guys remember what the range of a matrix is? the range of a matrix is AX, right? So you take any matrix A and you multiply with some X that belongs to your subspace. AX will give you your range of the matrix. How far can you reach with this coefficient matrix A, right? So AX will define your, for some X, that will define your range. Now, how can you represent that particular range as a basis, which means the smallest spanning set of linearly independent vectors? Can you do that or not? Well, actually, there are three ways to do this. So we are going to present over here three different ways to find the basis for the range of a matrix, and we will use the same matrix over here, A, which is 3 rows, 4 columns. So we are going to use the same matrix A. We're going to find its range, and we are going to find the basis of its range in these three, using these three methods. Some are easy, some require a little bit of work, some actually require a little bit of argument as well. So proof is required there. So the first one is finding the conditions for AX to be AX equals B to be consistent, which means AX is my range, AX equals to B has to be consistent, right? So if I want some B, when I take X and I multiply with any vector in my range, I should get some B. If I multiply it with some X that belongs to my subspace, I should get some vector that belongs to the range, which means AX equal B has to be consistent. The next one is to just look at some of the columns of A. Directly, you can get the basis for the range, but those columns correspond to the leading ones, and we'll take a look at that. And the last one, we will try to row reduce the transpose. Instead of reducing A, we'll try to reduce A transpose and look at the row space. Okay, so let's start with method number 1. So let's try to find the conditions for AX equals B. We are given this example X, right? We are considering that matrix X, and we are trying to find the basis for the range of A. First method, AX equals to B has to be consistent. So what we'll do is we'll form an augmented matrix. I have my A over here, which is right there, and then I'm going to assume B to be some B1, B2, B3. B1, B2, B3 will have to belong to the range of A, right? So this has to belong to the range of A. After I form the augmented matrix, I will do row reductions. I have over here a row reduced echelon form. So row reduced echelon form, my leading ones are over here, and there are no other non-zero elements in there. All the other elements in those columns are a 0. So I have over here a condition. What is that? 0, 0, 0, 0. That has to be a 0 for it to be consistent, right? So that is going to define my range. My range is not going to be all of R cubed, right? You cannot pick any B, any B1, B2, B3. You have to pick, in order for it to be in the range, you have to pick B such that B3 equals B1 minus B2. So that particular B is going to belong to the range of A. So you cannot pick any B here. If it has to be consistent, then it has to have this particular criteria. The last element in B3 has to be B1 minus B2. So what we can say is the range of A is going to be set of B's that belong to R cubed, where B is B1, B2, the last element has to be B1 minus B2, right here, to make it consistent. So you can rewrite this as what? You can rewrite this so that we can get a basis. So you're writing B as B1 times 101, right? So how much B1 do you have over here? 1, nothing, and 1, right? Over there. And then how much B2? Nothing, 1, negative 1, right there. So this is going to be a linear combination. What are my basis vectors? This guy and this guy, right? So that gives me a basis of 2 linearly independent vectors that span entire range, right? So you can take any linear combination of these two guys and get consistent solutions to that system of equations represented by that augmented matrix. And it is very easy to see that this is linearly independent, right? You have a 1 here, you have a 0 there, and you have a 0 here, you have a 1 there. So it's sort of an identity matrix that is embedded in my basis vectors, and the same sort of argument as we did for unit vectors being linearly independent, that applies over here. So you have got a basis of 2 vectors. So the question here was what? Find the basis of the range of a matrix. We took the matrix, we found the range, and the basis turned out to be 2 vectors in R cubed, 1 and 2. So that's your first condition, first way of doing it. We'll try to look at another example. So we are going to consider a different A, and we'll try to, the only difference over here is this is going to span all of R cubed. So you will get a consistent solution no matter what B you pick. In the previous example, you had some limitations on B. Here, you will not have that limitation on B. Let us try to take a look at how that would look like. So you have A over here, which is a 3 by 3 matrix. We are going to do the same thing. We are going to form that augmented matrix as A and B, right? A and then B is right here. So we have got A there, and then some B1, B2, B3. We will row reduce it. When you row reduce it, what do you have? Leading 1, leading 1, leading 1. That's it. So this will tell you that no matter what you pick for B1, B2, B3, you will get a consistent solution. So X, the X3 will be that, X2 will be that, and then you will have some condition X1 minus X2 plus 2 X3 will be B1, so it will give you what X1, X2, X3 are going to be. So what this means is this is going to be consistent for any B that belongs to R cubed. You're not going to have any conditions, which means that you can take any B, right? So now the range is going to be defined as a set of B's that belong to R cubed, where B is any B, so B1, B2, B3, pick any one. And how are you going to represent it as, you need to find the basis, right? So that basis, any B1 can be obtained by taking B1 multiplied by unit vector over here, which is 1, 0, 0, plus B2 times E2, 0, 1, 0, B3 times E3, 0, 0, 1. That's how you would get to any B, right? So your natural basis, right? These are your natural bases, E1, E2, E3 is going to be the basis in this particular example. So we have a natural basis. 3 vectors that are linearly independent and span all of R cubed. That's my basis. So here my answer would be that, and that. That's my basis. So this was another example, so a different A. The only difference is earlier I had a criteria on B. Next example, I didn't have any criteria on B. All right. So that's your first way of finding out the basis for the range of the matrix. Next is going to be very, very simple, but it's a little bit difficult to sort of prove. But it's easier than the first one. So a subset of the columns of A, not all the columns of A, but a subset of the columns of A will give you the basis of the range of the matrix. So what we'll do is, we'll take a look at row reducing the original matrix A with a homogeneous right-hand side. So in the second example here, we don't have AX equal B. We are using a homogeneous set. So we are looking at AX equal 0 here. We have the same A as we had, 3 by 4. And now we are forming the augmented matrix. The right-hand side is zeros. If you take this and row reduce it, you get that. Now, if you look at where the leading ones are over here and here. There are only 2 leading ones. The last row over here is a 0 row, right? So that doesn't count. You don't have a leading one there. So wherever your leading ones are, the columns that correspond to those particular leading ones are going to be your basis. So what does this correspond to? It corresponds to this guy. So let me just point that out. This corresponds to the first column, and then this corresponds to the third column, right? So these 2 columns, the first one and the third one, are going to form my basis. So over here, the range is defined as y's in R cubed, right? AX. You can take this A. this A and you multiply with x, any that x has to be from R cubed, and that's going to define my range. All right, y belongs to R cubed, such that y is going to be some amount of first column there and some amount of the third column there. So the basis over here is going to be 1, -1, 2, and 2, 2, 0. So it's sort of very directly we can do this. All we have to do is go from the augmented matrix of the homogeneous set of equations to the row reduced echelon form, mark out the leading ones, pick the corresponding columns, and that will be your basis. So I hope you guys are noticing that because I'm using the same matrix A, I'm always my example matrix is A, right? No matter which method, one of the three methods, I'm getting a basis with only two vectors. You see, earlier example, I had basis in which I had two vectors. Basis, I had two vectors. So this is sort of connecting the dimension. The dimension of the basis can only be one value. The number of vectors are going to give us the dimension. We'll see that topic slightly later in the lecture. All right, so the basis is this. Is it linearly independent? Is it a spanning set? Yes, if you take these two vectors and any linear combination of the vectors, you will be able to reach ax equals 0, right? You will be able to reach all the y's. Next, are they linearly independent? Yes, they are linearly independent. You see this, there's a 2 there, there's a 0 there. So for that to be linearly independent, that 0 will make it linearly independent. All right. Let's see. All right, so you got the basis with the second one here, but this particular method, even though this is pretty straightforward to carry out, because you're just looking at the subset of the columns of A, wherever the leading ones are, so it's pretty easy to carry out. However, we need to prove that why does this subset work? So what we'll do is we'll let A have 4 columns. So what we'll start off with is, say A has 4 columns, A1, A2, A3, A4. These are 4 columns of A, and we are trying to go for the homogeneous set of equations, right? So we are doing Ax equals 0. So what is that going to lead us? It's going to essentially mean that this equals A is A1, A2, A3, A4 multiplied by x. What is x? x1, x2, x3, x4. That has to go to 0. So if you carry out the matrix multiplication over here, x1 times a1, x2 times a2, x3 times a3, x4 times, that has to equal zeros, right? So this is a 0 vector in R to the 4. So this is 0, 0, 0, 0 here. Actually, no. This is we don't have any constraint on the number of rows in each column. So this is in general, right? So let me erase this. There's no constraint over there. So each of these columns can be anything. So our system of equations was Ax equals 0. That is going to be equivalent to requiring this, right? So the question is, if you work with that subset, you should be able to take some amount of first column, some amount of second column, some amount of third column, some amount of fourth column, and be able to go to 0. But the real question over here is, because we only took the first column and the third column, what happened to the second column and the fourth column, right? That's the question. Why didn't we not consider second and fourth? Because we will soon prove that the second and the fourth column actually depend on the first and the third column. A2 and A4 will actually turn out to be linear combinations of A1 and A3. And because of that, you don't really need to write A2 and A4. You don't need to consider those two columns. So let's try to look at that with the final row reduced echelon form of our augmented matrix of the homogeneous set of equations was this. You had that matrix there. So what it gives you equations. What is that? Well, this is 0, so that's fine. And then it will give you x3 minus 2x4 equals 0. So you've got that. And then the first one will give you x1 plus 3x2 plus x4 equals 0. So you've got that, right? So those are the two equations that come out of that row reduced echelon form. And from now, what you can do is, considering x1 and x3 to be leading variables, you can pick any value for x2, x4, and get the corresponding values of x1 and x3. So let us assume that you have x2 as some s, x4 as some arbitrary value t, then x1 needs to satisfy this, so it has to be negative 3s minus t, and x3 has to be 2t. So if you say take s to be a 1 and t to be a 0, what do you get? You get x1 to be a negative 3, x2 to be a 1, and both x3 and x4 to be a 0. So if you substitute that back in that condition, what do you have? You have, right, you have x1 was negative 3. So negative 3a1, x2 was 1. So plus a2 plus, what do you have next? Nothing for x3, nothing for x4. So 0 here and 0 here equals 0, right? So if you rearrange this, what do you get? You get a2 equals 3a1, right? So the second column actually is 3 times the first column, which is why it cannot be in my basis. Because remember, basis has to have linearly independent vectors. Over here, a2 depends on a1, so it cannot belong to my basis. Which is what we are trying to find, right? Basis for the range of the matrix. So we got this condition over here, a2 equals 3a1. And you can sort of go back and check whether that is true or not. a1, a2, right? You multiply this by 3, you get a2. So you can quickly check that. Next, what if you did, let's focus on a4 now. Why don't we need a4? Well, if you took the same set of solutions, but instead of plugging 1 and 0, if you did s equals 0, t equals 1, then you will be able to represent a4 as a linear combination of a1 and a3. Which means both of these two conditions combined, a2 is linearly dependent on a1, a4 is linearly dependent on a1 and a3, which means that a2 and a4 are linear combinations of a1 and a3, right? So if I have a1 and a3 in my basis, I don't have a2 and a4 in my basis. So let's try to see if you can reach to any b, right? So what I can do is add a slide here, and I can say, let us pick some example b. Let us say that I have a b that belongs to the range of a, and let me say b is some ax, right? Some ax. So I will say this is, say, 2a1 minus 5a2. I'm just arbitrarily picking up the values here, plus a3 minus 4a4, right? So suppose I had my b as this. Can I get to it with just a1 and a3? Well, let's try to look at this. a2 was what? a2 was 3 times a1. Okay. And a4 was a1 minus 2a3. So if I substitute that, what does this equal to? I get 2a1 minus 15a1 plus a3 minus 4 times a1 minus 2a3, which equals what? I have 2 minus 19. So I got negative 17a1, and then 1a3 plus 8. So I've got 9a3, right? So b, right, b that is belonging to my range, I was able to just use a linear combination of a1 and a3 and get there. Which means that a1 and a3 has to be in my basis. I don't need a2 and a4. Those are linearly dependent on a1 and a3. So don't have A2 and A4 in basis. All right. Questions about this? So this essentially proves that we can take take the columns in the original matrix, right? Take the columns in my original matrix that correspond to my leading variables, and that will define my basis of the range of A. So this is basis of range of A. Two vectors. Let's see. If I go back, all right. The third technique to find the basis of the range of the matrix is by row reducing its transpose. So what do we know about the range of a matrix? Range of the matrix is column space of A, right? So we know that from the definition of range. Range equals column space of A. Range of A is column space of A. So that means linear combinations of columns of A that will define your range of A. So column space of A is also going to equal row space of A transpose, isn't it? If I switch the rows and the columns, then the column space of A will become row space of A transpose. So that's what we are doing here. We are looking at the transpose. We are trying to find the base. Instead of finding the basis of, we were trying to go for the basis of range. Basis of range can be the basis of the column space of A, or it can also be the basis of row space of A transpose. So we are looking at this particular strategy over here. So that's what we are stating here. The range of A is the span of the columns of A, which is equal to the span of the rows of A transpose. No, not the row space, right? Column space, yeah. So we have seen that the row reductions doesn't change the span of the rows, right? So when you do row reductions, you get to a row equivalent matrix, and we have seen when we were going through the discussion on range of a matrix, we saw that row reduction doesn't change the row space, which means it doesn't change the span of the rows. So if let's start to row reduce A transpose instead of reducing A, because we are looking for row space of A transpose. So we are taking the same A that we had, 3 by 4 matrix, we did a transpose, so it became 4 by 3, right? So the rows in those columns have switched here. Now do the row reduction on this. What do you have? You have this row reduction. You can go even further to get this. Now if you look at this guy, you have what is the row space here? Row space has 1 and 2. These are the two vectors in my row space. So the span of these two vectors is going to define the range, right? So the range of A has two vectors. Essentially, this guy is my first vector there, and then the second vector here is there. They are linearly independent, and they are going to span all of my range, which means that these two vectors will form the basis of the range of the matrix. So the strategy that we applied over here is, instead of looking at A, the column space of A, we looked at the row space, the span of the row space of A transpose, and we leveraged the fact that row reductions don't change the row space. So if you want the range of this guy is going to be, if you want the range of A, it's going to be the same as row space of A transpose, defined by span of these two. So any linear combination of these two vectors, you will be able to get to anywhere in the range of A. So these three strategies actually gave me the same basis, right? How many vectors do I have in the range of A over here? Basis of range of A has two vectors. Again, I ended up with two vectors, exactly. So no matter which strategy I apply, my basis is getting me two vectors that are linearly independent, and they're spanning all of my range of A. But they are not all identical. But if you notice, there are some things that you can piece out of this, right? For example, I'll show you guys all three at a later stage. They are not exactly the same. In fact, if you take a look at this, if you go one step ahead, this is not in the reduced echelon form. This is in echelon form, but this is not in reduced echelon form. You can add the first row and the second row to get to the reduced echelon form. And if you do, the span, the basis is going to change slightly, but that basis is going to exactly match a basis from an earlier method. So in order for it to qualify as a basis, it doesn't have to be unique. What it has to have is linearly independent vectors that span all of my range. Or for a basis, in general, it has to span all of the defined subspace. However, the number of the vectors in the basis has to be constant, right? That's unique. Always going to be 2 for a given matrix A. All right. So these are your 3 ways of finding the basis of a given matrix A. Now let's talk about coordinates. Coordinates are essentially going to be how much of each basis vector do I need? So let me just write this down. Let's see. Coordinates are how much, as a linear combination, how much of each vector, each basis vector should we take to reach any vector in subspace. So in our example over here, the subspace that we are considering was the range, right? So in our example, we are going to check whether we can get a linear combination of the basis vectors to get to the range of A, right? So how much of, so the question really is, these two form the basis of the range of the matrix A that we considered as our example. How much of this and how much of this do I need to reach any vector that belongs to the range, right? So that's what you're trying to find out. So that's sort of unique way of representing. You can only do this, the coordinates will be unique for a given basis. You can only take some amount of the first one and some amount of the second one. Those amounts are going to be unique for the given basis. If we had 3 different bases, we are going to get 3 different coordinates, and we'll try to take a look at that. So let's try to start with, we'll do an example later on for the same matrix A. We'll try to find its coordinates for the 3 different bases that we got. But before that, let's state what coordinates are. So let us start with a set of vectors B over here, and this is forming my basis for the subspace W. So this guy has R vectors. This should be underlined because this is a vector here. So now the small w is a vector that belongs to my subspace W, and they are scalars d1, d2, d3, and so on up to dr, so that any vector w in cap W can be written as a linear combination of all these vectors. Why? Because it's a basis, right? So if this set is a basis, then we know that I should be able to reach anywhere in my subspace by taking a linear combination of these vectors. So I'm just considering one arbitrary vector here in the subspace. Can I reach that? Yes, I can. If I did a linear combination using these scalars d1, d2, d3, and so on to dr with those basis vectors v2, v so on up to vr, I will be able to get to that. That's because of this statement there, basis for W. And because it's a basis, I also know that v1, v2, and so on up to vr are going to have to be linearly independent set of vectors. So that's stated over here. Because B is a linearly independent set, right? It's a basis, so it has to be linearly independent. Because B is a linearly independent set, this representation is going to be unique. You can only take that d1 amount of v1, that d2 amount of v2, and get to W. There are no other ways of getting to the same W. There is going to be a unique d1, d2, d3 that will make that happen, because v1, v2, and so on up to vr are linearly independent vectors because they are a basis. So those values scalars d1, d2, and so on up to dr, those are defined as the coordinates of w with respect to the basis b. So in our case, if you have three different bases, we are going to have three different coordinates for that, and we'll try to do that as an example. So next question: why are coordinates unique? Right? Why can you only take that specific d1, that specific d2 to reach to that w? Why are they not other ways of reaching the same w? So what we can do is we can try to do this by sort of contradiction. So let's assume that there is that new set of vectors that exists, right? Not d1, d2, dr, but by contradiction, let us assume that there are other scalars that satisfy this. So I'm saying w can be expressed as some new b1, v1, new b2, v2, and so on up to new br, vr, right? Let's just assume that is true. If you subtract equation 1 here and 2 here, what do you get? W minus w gives you the 0 vector there, and all the coefficients of v1 over here is going to be b1 minus d1. So you're sort of doing, this is 2, this is 1, you're doing 2 minus 1 to get this, right? So you're getting b1 minus d1 for v1, b2 minus d2 to v2, and so on up to br minus dr to vr. And because it is linearly independent, because the set B is linearly independent, we know that the only way it can be linearly independent is if each of these coefficients of the V's are zeros. So you must have the D's equal to the B's because of the fact that these are a basis. So all of them are linearly independent. There is no other way of doing it. So for all j, 1 through r, all the d's match the b's, which essentially means that this representation is going to be unique. All right, let's move on and look at the example of coordinates. We'll look at the same matrix A, and we will try to randomly choose some vector x, right? So this particular vector over here has been, say, randomly chosen. I've got my A same as before, the example matrix. We found its range, we found its basis of range, we did all of that. So we are trying to say A, if you multiplied with x, you get this particular vector over here. That's our B, right? Can you guys tell me what this B belongs to? You did AX. So what does this B belong to? It belongs to R cubed. But let's see, does it belong to the null space? Does it belong to the range? Does it belong, what does it belong to? Range, exactly. Right, that's how we are defining range. For some x, if you do ax, you have to be in the range, right? That's how we define range. So if you choose randomly choose this particular vector x over here, when you do ax, you will get a vector b that belongs to the range of this vector matrix A. In this case, we got 3, 9, and -6. We found 3 bases for the range of A using our 3 methods. With the first method, our basis was 2 vectors. They were always 2 vectors, but they were different 2 vectors. The basis was 1, 0, 1 and 0, 1, 1. So how much of this vector and how much of this vector should you take so that you can reach to this B, right? That's the question. The answer of that will give you the coordinates. So 3, 9, 6, that's your B that belongs to the range of A, can be reached by taking 3 times the first basis vector and 9 times the second basis vector. And you can sort of clearly see that this is going to be okay, right? So there is a 1 over there, there is a 0 over there, so I definitely need a 3 there, right? To get a 3 there, I definitely need a 3 there. So it has to be 3 times the first vector. And let's try to use the 0 here. The second element is a 0 there. You need to get a 9, so this has to be a 9, right? And then using those two, you can check, essentially proving that these are going to be linearly independent as well, right? The basis vectors. And let us try to see if the last one matches up or not. 3 times 1 plus 9 times -1 will give you -6. So yes, 3 times the first basis vector, 9 times the second basis vector will give you something that belongs to the range, which means that the coordinates over here are going to be 3 and 9, right? Those are the scalars, d1 and d2. Coordinates for this basis, right? It's going to be a different one for the different basis. Let's see. Similarly, if you took the other two methods, our second method, which was what, subset of the columns of A, we are trying to reach the same B here, which belongs to the range of A. Our basis vectors were this and this. Again, because of this 0, you know that they are going to be linearly independent. Can you find the constants? Can you find the scalars? Well, over here, you will get -3 and 3 as your coordinates. So when you take d1 times first basis vector and d2 times the second basis vector here, you will be able to reach a B that belongs to the range of A, which makes these two guys your coordinates, different from the previous one, right? Here you had 3 and 9, you had a different coordinates for when you change the basis for the same matrix A. Next, our third method here, which was to find the row space of A transpose, gave us this as your basis. So you need 3 times the first vector here and 12 times the second vector here to get to the same B. So the coordinates over here are going to be 3 and 12. Now, let me just show you guys the basis, right? So the basis, there is a relationship. They are all, the three methods gave us 3 different bases. However, and they're all linearly independent and they all span the range of A. But they're all different, right? So, but there is a way to check whether they are sort of giving us the same information, but they are also linearly independent. Let's take a look. 1, 0, 1 and 0, 1 and -1, right? So if you did over here, if you added them up, what would you get? Right. So let's take a look at adding these two guys up. If you add them up, no, let's do subtract, right? So if you did this guy minus this guy, what do you get? 2 minus 1, you get a 1. 2 minus of -1, you get a 2, and then you get a -2. All right, no, that's not going to work. All right, then let's do a simple one. Add this and this, right? If you add these two vectors, what do you have? 1, 0, and -1, right? And 1, 0, and -1 is right here. 1, 0, and -1. No, it's not here. Did I do something wrong here? By taking, they're all linearly independent, but they're all sort of spanning the same set, is what I wanted to say. So linear combinations over there, you will be able to get to the same one. So I think if it is, you have a -1 there. If you add these two guys, you get a 0 here, right? Yeah, if you add these two guys, what do you get? You get 1, 0, 1, which is your first vector there, right? Like that, you can find relationships between those basis vectors. They are all linearly independent sets, right? This independent from this independent from this, but they're not all unique, is what I'm trying to say. You don't get all unique. Okay, questions about this? Questions about how do you find the coordinates for a given basis? You just need to be able to express it as a linear combination. Some amount of this, some amount of that. What are those amounts of the basis vectors? That will tell you the coordinates. You're going to have different coordinates for different bases. So coordinates in the other basis for the range of A. All right, let's move on to dimension, our next topic. So dimension, we are used to thinking geometrically, and dimension sort of follows that same intuition. So if you look at the dimension of Euclidean space R squared, you know that that dimension is going to be 2. And if you look at the dimension of R cubed, that dimension is going to be 3. How about for a line or a plane? For a line, the dimension is going to be a 1, and for a plane, you would need two vectors to span a plane. So the dimension over there is going to be 2. What we want to do is we want to extend this same idea to higher dimensions. And we want to be able to do this even if we can't do it geometrically. Let's try to do this algebraically. And dimension is pretty simple. If you know the basis, just count the number of vectors in the basis and you know the dimension. So dimension is sort of defined as cardinality of basis. Or we will later define as the same way of saying it is going to be the dimension of a subspace W is going to be the number of vectors in this basis of W, right? So when we were looking at the basis for the range of the matrix A, we always got 2 vectors. No matter which basis, there were 3 different bases, but we always got 2 vectors. So the dimension or the number of the cardinality or the number of vectors in the basis was always 2, telling you that dimension of that particular subspace, which was the range of A, was always 2. We will show that every basis will have the same cardinality, right? So we had 3 different bases, but they all had the same, for the same matrix A, for the same range of A, you had the same cardinality, 2 vectors every time. Every basis of this subspace will have the same cardinality. This cardinality is equal to our geometric intuition of the dimension, and we'll take a look at that. So that's how we would define it. Look at the number of vectors in the basis. And in order to qualify as the basis, they have to be the smallest spanning set with linearly independent vectors. So let's take a look at this particular example over here. Here you have a plane in 3 dimensions, and let us say that you have 2 vectors u and v that span all of this plane. So the plane over here shaded is span of u and v. So any linear combination of u and v, you will be able to span all of that plane. So what is going to be, how many vectors do you have in your basis? Well, u and v, right? So because you need 2 of them to be a plane, right? So if you had only 1 of them, you could go up and down. That would give you a line. It would not give you a plane, right? So if you have the dimension of 1, then you can only go in a line. But if you want a plane, then you would need 2 vectors. And that would give you, say, 2 vectors in basis implies dimension of 2. All right. So let's take a look at some examples of the range of the matrix over here. So recall our previous example for the range with this particular A. When we looked at the range, we found that there were 3 bases. One was this, the second was this, the third was this. Using 3 different approaches, you got 3 different bases. Not necessarily, right? Now it's not necessary, but we got 3 different bases over here for the same range of A as our subspace. Note that they are exactly 2 vectors. 2 vectors in R cubed every time, right? So our dimension over here is going to exactly be 2. The range of A is going to be a plane containing the origin, right? So we saw that if that plane doesn't contain the origin, then it would not qualify as a subspace. But over here with 2 vectors, you will be able to you will be able to span the entire plane with the origin, containing the origin. All right. So all bases have to have the same cardinality. So the number of vectors in the basis have to be the same for a given subspace. So no matter how many bases do you have, right? Like we had 3. What if you have more bases than that? No matter how many bases you have for a given subspace, you need to have the same cardinality, same unique dimension. Again, we'll try to prove this by contradiction. So what we'll do is we will try to start with a subspace W here that is of R to the n, that belongs to R to the n. So B is a basis there. B is a set of vectors v1, v2, v3, and so on up to vr. And S is another set of vectors u1, u2, so on up to us. And let us assume, right, we want to prove this by contradiction. So we are assuming that there are two bases of different lengths, right, different cardinalities. One has a cardinality of R, the other one has a dimension of S. They are different. There are two bases. So when there are two bases, if you are defining them as bases, then I know that they are all going to have to be linearly independent there, and all the U's have to be linearly independent over there. Now, what we want to prove is R equals S, right? For it to have the same cardinality, same dimension, then we have to prove that R equals S, so that the two bases are going to have the same cardinality. So you have a subspace W, and that subspace has a basis. We are actually defining two bases, two different bases with different number of vectors, which means different cardinality, different dimensions. What we are going to try to prove by contradiction is that no, they are not different sizes. You actually have R equals S. You should have R equals S. So what we'll do is we'll start the proof by contradiction. So we are going to assume without any loss of generality that R is smaller than S, right? You could go the other way, but then you can switch around B and S as well. So we'll just start with R is less than S. So the number of vectors you have in this basis is less than the number of basis vectors you have in S. What we are assuming here is B is a basis, and we are going to try to show that S is linearly dependent, right? So if it has to be a basis, then you need linear independence between the vectors. So if it is dependent, you know that it is not going to be a basis, right? So what we are trying to prove here is this. B is a basis. S has more vectors, right? S is more. So you have more vectors in S. S has more vectors than B. And what we want to prove is, S is linearly dependent set. So if it's a linearly dependent set, it will not qualify as a basis. You will have to go down to the smaller one. What is that? With R vectors, what is that? Set of B, right? B will be your basis. So you can say that in other words, S can't be a basis for W subspace. So let's try to do this. You look at every vector uj, right? U sub j is any vector in S. Uj that belongs to S is also going to be in W. Because we said that W is the subspace for which this is the basis, you should be able to take any vector in B or any vector in U and be able to span W. So you can write this statement: W equals span of S, which should be equal to span of B. Any linear combination of the V's or any linear combination of the S's you should be able to get to anywhere in the subspace W. Should span that subspace. So it can be represented as a linear combination of the vectors in B, right? So we are trying to represent the U's as a linear combination of vectors in B because their spans are the same. Remember, we are trying to prove this by contradiction. So what we can argue is that the vectors in S are going to be linearly dependent, and we'll show the algebra that corresponds to this on the next slide. What we will end up with is a homogeneous set of equations with R rows, less rows than variables. We'll have more variables, less rows. So we are going to have non-trivial solutions that exist, which is going to make this linearly dependent. So you see what we'll end up with is something like this. You will have a homogeneous set equals 0, right? Whatever that is, a homogeneous set. What you will end up with is R over here, S over here. So R is less than S. When you carry out this, the solution for this homogeneous set of equations is going to have non-trivial solutions, because we saw that when you have a homogeneous set of equations in which you have less equations than unknowns, then you are going to have non-trivial solutions. Obviously, the trivial solution is going to be there, but you're also going to have the non-trivial solutions here. Let's try to look at the math behind this. So what we are doing here is we are just recapping. B is our basis with R vectors, S is our basis of the subspace W with S vectors, and R is less than S. Number of vectors in the basis are different. So that's what we had assumed. Later, we try to express each U as a linear combination of the V's, because span of B has to be the same as span of B, span of S. They have to be the same. So what we can write is each vector in S written as a linear combination of all the vectors in B. So U1 represented as a linear combination of the V's, U2 similarly, US similarly, right? So this is so on, all of the way. So if that is the case, in order for us to determine whether S is linearly independent or not, we'll try to solve this particular homogeneous equation. Are there any x1, x2, x3, and so on up to xs such that the linear combination of all the u's will give me a 0? We'll try to see if that is true or not. And if that is true, we know that that is going to be a linearly independent set. If that cannot be true, then we know there is linear dependence. So in order to do this, what I'll do is I need to multiply each u with x1, right? So I'll do x1 over here. This guy I'll multiply with x2, so on up to I'll multiply this guy with x, not 3s. So if I'm multiplying the left hand side, I'm also multiplying the right hand side, right? So all of this is being multiplied by x1. All of this is being multiplied by x2, and so on up to all of this is being multiplied by x3, right? And that the equation that we are setting it up as this equals 0, this equals 0, this equals 0, right? So if you do some manipulation over here, if you look at the coefficients of the multiplier for V's, what are you going to get? You're going to get a11x1, which is a11x1 plus a12x2 plus a1s x3. They are all getting multiplied by the V's. So if this has to give you a 0 over there, then all of these are going to have to go give you a 0 over there, because the fact that B is linearly independent. We said that if B is linearly independent, then all the V's are going to be all linearly independent. So the only way is to get them to be a 0. So that is by looking at this. If you look at V2 here, the multiplier for V2, what do you have? A21x1 plus A22x2 and so on up to A2s xs here. Will also go to 0. So right, that's right there over here. And then so on up to the last one. So in this case, what do you have? You see the number of rows over here are R, and the number of columns over here for this are S, right? So if you set it up as a AX equals 0 problem, then you will have number of rows to be smaller than number of columns over here, because R is less than S, which essentially means that you have a trivial solution, right? All the x's are 0, but you also have, because of the R being less than S, you are going to have non-trivial solutions. Exactly the same reason why we had non-trivial solutions when we had a homogeneous set of equations which was consistent with more equations than unknowns. Less equations than unknowns. So what this means is vectors u1 through us are going to be linearly dependent, which makes your S not a basis. So, another way of looking at it is whatever is the smaller set, that is going to be your basis for a subspace. The bigger set, in this case we said this guy, right? The bigger set is not going to be your basis, right? So the smaller set will be your basis. Or you can just twist this around. If in fact S is the basis, then B will not span the entire set, right? Then it's not going to be the basis in that case. All right, let's move on to the definition of dimension. We talked about this. Dimension is essentially equal to the cardinality of any basis. So you essentially look at the number of vectors in the basis, and that is going to be defined. That's going to define dimension of a subspace W. This is well defined. Every basis will have the same cardinality. We just proved that, and it also agrees with our geometric intuition for R squared, R cubed, and so on, and their subspaces. If you have a zero vector, for example, its dimension is going to be 0 because there are essentially no vectors in there for which you can take a linear combination. So for that particular zero set, you are going to have a dimension of 0. All right, let's take a look at some relationships between dimension, spanning set, and linear independence. And some of these topics we have already seen. So this will be a quick review of that. So suppose you have a W, which is your subspace in R to the n, and let us say that dimension you have as P, right? If that is the case, what can we say about the basis in which you have more than P vectors? So if there is a set over here which has more than P vectors, like we assumed earlier with S vectors, where S was greater than R. If you have more vectors, then you're going to end up with that subspace which is linearly dependent, right? So that set with more than the dimension vectors, more than the number of vectors that are linearly independent, you're actually going to get linear dependence over there. Just as we saw linear dependence with U, right? Because S was more than R. Let's go back. But if you have fewer, that means that you do not span the entire space. Fewer than the dimension, if you have that set, then you're not spanning the entire span. You're not spanning the entire subspace. If you have exactly P and the dimension is P, then you know that those P are going to be linearly independent vectors in the subspace, and they will span all of the subspace W. If you have P vectors and they are spanning W, then they must be linearly independent. They will be the basis. Any set of vector that is not linearly independent spanning must have the cardinality P. So this is essentially saying that if you have independence, then you must span the entire space, and you will need P vectors for doing this, and P will be your dimension, the number of vectors in the basis. What about if you wanted to extend out the basis? How many vectors do you need? Well, basis is your smallest spanning set. So if you increase the number of bases, the vectors in your basis, you can extend out your basis to a bigger subspace. So if you have a set of vectors over here, R of them, such that R is less than P, and let us say that this is linearly independent vectors in subspace W, you can extend out the basis. S can be extended out to a basis with P vectors for W. What we are doing over here is essentially adding more vectors to a basis, and if you do that, you essentially extend your basis out as well. You will be able to span a bigger subspace. All right, let's talk about the rank of a matrix and nullity. So this is going to be very straightforward to look at. What is a rank and what is a nullity? Rank is defined as dimension of the range of A. What is the range of A? The range of A is going to be the column space of A, right? So if you can find the column space of A, you look at the basis, number of vectors in there is going to give you the rank. So for the rank of this particular matrix A that we have considered so many times, we had the dimension of the basis of range of A to be a 2. So the rank is going to be 2. And no matter which method we use to find the basis for the range of A, we always had 2 vectors. So the dimension over there for a particular matrix A is going to be unique. rank is dimension of the range of A, right? So you take the range, you find the basis of the range, and the number of vectors in that basis will give you the rank. Nullity is going to be the dimension of the null space. So nullity for a given M by N matrix A is going to be the dimension of the null space. So you find the null space, you find the basis of the null space, and the number of vectors that are in that basis will give you the nullity. So if you have the same A over here that we have been seeing as an example, if you do the row reductions and get this final reduced form of AX equals 0, the homogeneous set of equations, the equations you will have these, the solutions will be those, the null space can be written as S times this basis vector plus T times this basis vector. So you have essentially two basis vectors in the null space of A, which makes the nullity of A equal to 2. Some theorems about rank and nullity. So if you have a matrix A that is M by N, the dimension of the row space of A is going to equal the dimension of the range. And we'll take a look at this with an example. So row space of A, can you find the basis of this? If you find the basis of the row space of A, count the number of vectors in that. That is going to give you the dimension of the row space of A. That is going to be equal to the dimension of the range, which is the rank. So dimension of the range is, find the range, express that range using basis vectors. The number of basis vectors you need is going to give you the dimension, which is also equal to the rank. So in other words, the dimension of the row space of A is going to equal the rank of A. And we'll prove this by using sort of a numerical example in just a bit. Note that the range of A is going to be in the subspace of R to the M, right? So suppose you have A as M by N, and X is N by 1, and you get B equals M by 1, right? So the range is going to be AX. So the range has to belong, so B's, all the B's belong to R to the M, a different size Euclidean space than A. The range of A is going to be, right? The range of A is defined by B that belongs to R to the M, while the row space and the null space of A, which is defined by the X, are going to be in R to the N. So these guys are going to be in R to the N, a different Euclidean space. Theorem: nullity and the rank will sum to N, where N is the number of columns in the matrix. So if you have A to be M by N, right, like last time, what did you have for A? A was 3 by 4, right? So our N was 4 over here, number of columns. What did we have for rank for this guy? We had rank of A go to 2, and we also looked at nullity of A on this slide is 2. And when you add these guys up, you get the number of columns in A, right? So the rank plus nullity will give you the number of columns in a matrix, which also means that you could have had something like this, right? You, for a different matrix, you could have something like 3 and 1. Let's go back here. All right. We looked at this? Yes, we did. Let's take a look at the row space. So I'm going to take a look at this particular statement here. Dimension of the row space of A equals the rank of A. Let's try to take a look at that particular statement with an example. So we have our A as our 3 by 4 matrix, same example as we have been seeing so far, for which we have found the rank to be a 2, so the dimension of the range and the dimension of the null space. Both were just happened as a coincidence, as both of them went to 2, and the rank plus nullity is 4, which is sort of the number of columns in the matrix A here. And when you row reduce this, what do you get? You get a row equivalent matrix in B. What is the row space? Row space is 2 vectors there and there, right? So here is your first vector, and that's written in my row space there, and the second vector over here, non-zero vector, is over here. That is my second vector in the basis of the row space written out in blue. So how many vectors do you have in the basis of the row space? Well, there are 2 of them. So the dimension of the row space is going to equal 2. So the dimension of the row space over here equals the rank, 2, 2, right? So this sort of validates that statement there. Dimension of the row space equals the rank, or rank is defined as the dimension of the range. All right, so this is it for the class today. I know that this was a lot of terminology, but I hope that with examples, we were we got some clarification about the various terms that we saw today. All right, I'm going to stop recording over here. Let's see, stop sharing.